Hey, so this is Joe, and this is the first video of the 12th chapter of Stewart's Calculus. So this is the beginning of differential multivariable calculus. And we start off this course basically talking about vectors and how they exist in three-dimensional space, because one important thing about three-dimensional space and thinking about points and functions and all that is that every point in three-dimensional space, you have to think about it as the terminal point of a vector that starts at the origin of that space. And I'm going to show you kind of what I mean about that later, but if you need a refresher, you've got a vector, so it's a directional value. It's a value that has direction. And so in 2D space, a vector, which you write with this notation, it's a symbol with a little arrow on top of it, just has two components. You have the x component and the y component, and they can be any values like that. And so in 2D space, when we have our x-axis and our y-axis, we have our x component of the vector and the y component of the vector that meet at a right angle, and that's how that works. However, in three-dimensional space, you have three components to a vector. So we'll write that A, and so you'd have your x component, your y component, and your z component, because there are three dimensions. And so in three-dimensional space, you should think of every point as, and so let me draw out a little coordinate system here, and we'll see this on the next screen. We're going to be using a lot of 3D graphing software for this course. But you have your x-axis, your y-axis, and your z-axis, and we're going to think of every point that we write in terms of those three axes as the terminal point, so the end point of a vector that starts at the origin. And that makes it easier to kind of conceive of functions in 3D space, and also these things called vector-valued functions that we're going to be talking about actually pretty soon in this course. And so, and the other thing that you're going to want to do when you're thinking in 3D space is to always kind of separate out this 3D space in terms of three two-dimensional coordinate planes, three planes. And so I'm going to show you what I mean in this next slide right here. Okay, so let's say this is a little bit of an easier space to deal with and kind of think of how to represent points in 3 dimensions. But so let's say that one little tick here is 1, and we have our x-axis, our y-axis, and our z-axis, and this is kind of the conventional way to look at things. And you have our x-axis is the positive part, and the negative part over here. Y-axis is the positive part, and the negative bit's over there, and that's the positive z-axis, and this is the negative z-axis right there. Whoops. And so let's say we have a point that's 1, 1, 1. Well, when we plot that, we'd go out 1 on the x, then we go out 1 on the y, and then we go up 1 on the z. And so we'd be kind of out here, and we want to think of that as the terminal point of a vector starting at the origin. And now let's say we have a point -2, 2, 3. So we'd go -2 on the x-axis, up 2 on the y-axis, and up 3 on the z-axis, and we'd end up somewhere up there, and that would be the terminal point of that vector. So that's how I'm going to recommend that you conceive of plotting points in three-dimensional space, because if we think of them as vectors, a lot of the operations that we're going to have to do later on to learn things about relationships between points and functions of points in 3D spaces is going to be made a lot easier if we can use a couple of operations that are specific to vectors, namely the cross product and the dot product, which I'm going to talk about in the next 2 videos after this. But right now, I'm going to kind of give a little bit of refreshers, a couple refreshers on some of the operations that we've already learned how to do on vectors in 2-dimensional space in previous classes, like pre-calc. And I'm going to give some reminders on that and write out real explicitly the operations that you need to know for now, and then in the next 2 videos we're going to move on to learning some new things about vectors. But even if you've taken pre-calc, I'd recommend that you watch this video, because we're going to kind of construe some things about vectors in a new light and you're going to have to think about them in a way that you haven't done before, and that's going to make multivariable differential calculus a lot easier to kind of conceive of. Alright, so we've already dealt with vector addition / subtraction. They're really the same things, just the subtraction has a negative values. And scalar multiplication, we've dealt with that with two-dimensional vectors. And when we're using three-dimensional vectors or even four-dimensional vectors, which sometimes happen, you do the exact same thing as you would with two-dimensional vectors, however you just have a third component. So if we have a vector A, and from now on, when you write out the individual components of A, it's generally just a convention to write these components out as A sub 1, A sub 2, A sub 3. And so the same letter used to symbolize the vector, but with these numbers attached, and the 1 corresponds to the x component, 2 the y, and 3 the z component. And then we have a similar vector B, generally. And so if you were to add the vector A and the vector B, well, remember they're directional, so we're not just going to get a number, we're going to get another vector. And that will be the vector where the x component is the A's x component added to the B's x component. The y component of this new vector is going to be the A's y component and the B's y component, and the z component is going to be the z component of the A vector and the B component, z component, sorry, of the B vector. And graphically, I'll write out how we know about this in 2 dimensions, and it works the same in 3 dimensions. It's just more difficult to draw. Say we have some A vector here, we have some B vector here. One method of drawing this out is make a parallelogram out of these vectors. So we got another A and B, and then the A plus B is this vector here that connects the 2 points. And then we also have our triangle method. Say we have the same A and B vectors, and it's also called the tail to tip method. We've got the B vector, we've got the A vector right there, and then the resultant vector, which is these 2 vectors added, the A plus the B, connects them. So this is called the tail to tip method. And technically these 2 methods apply in three-dimensional space. However, three-dimensional space, it's always more difficult to do graphical analyses of things that can also be done algebraically, just because it's so much more difficult to draw and sort of think about. So from now on, whereas like in pre-calculus, the graphical methods are probably the easiest way of conceiving of vector addition. From now on, when you're in 3 dimensions, using the algebraic method is probably going to be a little bit easier. So thinking about it in terms of adding components is probably going to be the way to go for you. And then we also have scalar multiplication. And scalar multiplication is where you're just multiplying a vector by some constant, and all you have to do is you still get a vector out of this operation, and you multiply each component by that constant, and you get the new multiplied vector. So really all that scalar multiplication does is, say you have a vector A, all it does is A preserves its direction, it just gets either bigger or smaller depending on what this constant here is. Yeah, so those are the 2 operations that we've already dealt with before. And so now, from this, we can kind of deal with or use another way of expressing vectors aside from this notation here, right here, the bracket notation. There's another notation we can use, and we'll be able to conceive of it on the next screen. So there are these 3 special vectors. They're called the standard basis vectors, and they're 3 vectors that never change. And we call them I, j, and k. So the I vector is a vector where it's just 1 along the x-axis, and so we can actually draw these out. If we consider that to be the z-axis, this to be the x-axis, and this to be the y-axis, then the I vector is this vector out here that has a magnitude or a length of 1, and it just travels along the x-axis. We've got the j vector that is just 1 has a length of 1 along the y-axis, so that's going to be a j, and the k vector, which is just a 1 along the z-axis. So all these vectors are perpendicular to one another, and they all have a magnitude or a length of 1. So by multiplying these vectors by scalars and adding them in certain ways, we can actually express any vector. So let's kind of prove that. Let's say we have a vector A, and that's equal to 5, 4, 3, and that's our vector. Well, say we have, so if we add the I, j, and the k vectors, and so that means we add all their components. So let's do that. I plus j plus k, that's going to be 1, 1, 1, right? Well, if we multiply anything by 1, it's going to be that same number, right? So that means if we multiply, if we multiply each of these vectors that are added together by some other number, we'll get that number back as the component of this sum in the resultant. So if, say, we multiply the components of A by each of these vectors respectively, so let's say we have a 5i, a 4j, and 3k's, well then that vector will be 5, 4, 3, and that vector will end up being A. So what we have is if we have, we'll write this out generally, if we have some vector that has its components like such, like so, then we can express that vector as the sum of the I, j, and k vectors multiplied by these components. So the x component multiplied by the I vector, the y component, that's a 2, sorry, the y component multiplied by the j vector, and the z component multiplied by the k vector. And so we can express any vectors as a sum of some other vectors, and that just algebraically that'll help us a lot later on in this course. And so finally we have two more things to talk about. We have finding the distance formula of distance formula between 2 points in three-dimensional space. We have finding the magnitude of a vector or its length, and then we have unit vectors. So let's go do that right now. So your book has a proof for the 3D distance formula, and I'm not going to give that to you right now, but I'll kind of explain to you intuitively how it works. So if we have 2 points, P1 is x1, y1, z1, and P2 is x2, y2, z2, if we want to find the distance between P1 and P2, we take the square root of the difference between the x component squared, the y component squared, and the z component squared. And this is basically a three-dimensional Pythagorean theorem, if you think about it. Because if you think about the 2D distance formula, all it is the two-dimensional Pythagorean theorem. Because it's basically just this part of the equation, because we don't have any z components. This part is added on for 3D, the z's, but the x's and the y's, that's just the two-dimensional distance formula right here. And all that the two-dimensional distance formula is you have a point here and a point there, and you make a right triangle, find this component, the x, the y component, you square them, then take the square root of them, and then you'll get the distance here. Well, that's basically the same way that the 3D distance formula works. We just have one more component, and we have to factor that in this way. And if you draw it all out, you'll find you make multiple right triangles, and then you'll eventually reduce down to this formula. And your book shows that proof as well. And so from this formula, we can find the magnitude or the length of a vector. And the magnitude of a vector we express by writing these two bars around the side of the vector. And all we do is, if we have our components, we take the square root of the sum of all the squares of those components. And this comes from the 3D distance formula, because if you remember, if we think about a vector in 3D space as always beginning at the origin, there's an implied -0 here. Like, it's the distance between A1 and 0, the distance between A2 and 0, the distance between A3 and 0, and then that's squared, but we don't write the 0 because it's 0. So that's how you can kind of think of the formula for the magnitude of a vector. And so now that we know now that we have this magnitude formula right here, we can talk about unit vectors in 3D space. So as you might remember from pre-calc, a unit vector is a vector that is in the direction of some other vector, so they have the same direction, but it has a magnitude of 1. So vectors like this are helpful because we can multiply them by or not multiply them, use these other two operations that we're going to talk about in the next videos, by another vector, and since the length is 1, not much is going to change. But, and so they have a magnitude of 1. And so the way that we get to that, and your book again has a proof for this, but I'll give you kind of an intuitive explanation. So we have the unit vector of A, and this is one notation for a unit vector, a big U and a little a. So the unit vector of A, so the vector with a magnitude of 1 in the same direction as A, we write it as A over the magnitude of A. And so all this is scalar multiplication. We are dividing, in a sense, each component of A by its length, right? And so thereby, we're taking basically this vector, all its components are proportional. They still have the same proportions to one another as they do in A. So the direction of this unit vector is going to be the same as the direction of A. It's just the length we're changing. And since we're dividing these components by the length of A, the length of the unit vector, once we do our magnitude formula, so the magnitude of A is always going to end up being 1. And so that's how we find unit vectors. So that's it for this kind of first introductory chapter to vectors generally in 3D space, kind of a review video. And the next two videos, we're going to introduce two new operations. They're going to be the cross product and the dot product. So stay tuned for that. They're pretty interesting. And then in the next chapter after this, we're going to start getting into actually doing some calculus, doing some multivariable calculus. So stay tuned for this. This is a doozy of a course, but it's an interesting one. So yeah, thanks for watching.